All right, so we're going to solve a separable first order differential equation. And then we're going to solve differential equations involving growth and decay. And then we're going to do an application where we use Newton's law of cooling. A couple of things to be able to be good at or remember or use, applying properties of exponents and logs, and then the equation for continuously compounded interest, which we'll remind you of. Okay, so what is a differential equation? First order, separable, what is it? Okay, so a differential equation is an equation that has one or more derivatives in it. A separable differential equation is one in which all x and dx's are on one side and all the y's and dy's on the other. I'm going to separate them. A first order separable differential equation can be written in this form. Our job is to separate the x's and dx's from the y's and dy's. Okay, so we're going to do that first, separate. We're going to integrate on both sides with respect to appropriate variable. You'll see what that means in a second. We can write a general solution and then we can find a particular solution if it's necessary. Particular meaning we solve for that c that we always put, plus c, we can solve for that. Okay, let's look at this first differential equation we have here. Part A, we're going to actually find the general solution first. Part B says find the particular solution. Part C is find the particular solution, going through these different points. Okay, so let's go ahead and solve this craziness first. Okay, so my first job is I want to get my dx's and the x's together on one side, and then I want to get the y's and the dy's together on the other side. I'll maybe try and do these color-coded. So I've got 1 plus x squared equals dy, equals 2xy. So I'm going to move that over. Next, I'm going to write it as 1 plus x squared, and I'm going to leave the dy on the left because that's what it said, and move the dx to the other side. And now I'm going to divide both sides by, I want to get rid of that y, and I need to get rid of that 1 plus x squared. So I can multiply it all out, but it's easier if I just take the 1 plus the x squared together. So that will give us, on the left, we've got 1 over y dy, and then I have 2x over, let's change colour on that, 2x over 1 plus x squared dx. So now I have two separable differential equations, which now I can integrate both sides with respect on this side to y, and then on this side, I'll change the colours on just completely there, this y, and then in terms of x. Okay. Alright, so let's start. We've got the integral of 1 over y dy, nothing where you're there, we can do that, no problem. We're going to do the integral of, we've got this 2x over 1 plus x squared dx. We're going to have to do some u substitution here. So let u be 1 plus x squared. Derivative du dx is going to be 2x. I'm just going to move that dx up. So du equals 2x dx. So now I can see 2x dx, which is going to be my du. And I'm going to be left with 1 over y, or 1 over u, sorry. So integral of 1 over y dy equals the integral of 1 over u du. Now I just have to go ahead and integrate these. So that gives me the natural log of the absolute value of y on the left, and it's going to be the natural log of the absolute value of u, which is 1 plus x squared. And then since we're integrating this, and there's no limits, we need to put a plus c. And if it's confusing you or annoying you, let me just put a plus c there too. We'll see what happens with that in a moment. Okay. I have this plus c, c1, c2, and technically they can be put together and have a plus c altogether. So let's rewrite this as one big problem. Natural log of the absolute value of y equals the natural log of the absolute value of 1 plus x squared plus some c. Just put them together. Now, in order for me to try and solve this, because it says to find the general solution, solve for y, I have to get at the y, and that natural log is in the way. So in order to get to the stuff that, or get rid of the natural log, is I'm going to put both sides into the power for e. What does that mean? I'm going to put an e right here, e to the power of this, e to the power of this. So remember, this is base e, this is base e. the bit that's in the way here, we'll talk about that side in a minute. But on this left side, this just becomes absolute value of y. So the left side is not too bad. This right side is a little bit more work to deal with here. So this is going to be e to the natural log of 1 plus x squared, and then plus c. So in order to think about what's going on up here, just think really quickly about if we had x to the 5th, or to the power of 5 plus 2, let's say. We know that's x to the 5th times x to the 2nd. There's a multiplication going on there in there. So in order for us to break this up, I've got the absolute value of y equals e to the natural log of 1 plus x squared times e to the power of c. So I just broke this up with the same bases. Alright, so this is the absolute value of y. Remember, the base on this is just e, so it's e to the power of the natural log of e, which we know undoes each other. So we'll get left with the absolute value of 1 plus x squared times e to the c. It's still an unknown. It's okay, maybe the value e, or the number e to the power c. We don't know what it is. We can just write it as c. It's still an unknown quantity here. And if we remember, in order to know how to finish this up, we're going to have it written as just y. When we think about y, think about the absolute value of x plus 3. Let's say equals plus or minus 9. Then we would write that as x plus 3 equals 9. X plus 3 equals negative 9. So applying it to this, since we got rid of those absolute values, we can write this, it has to be plus or minus the absolute value of 1 plus x squared times c. Or we could put c first. Alright, that was quite a bit of math and applying properties of exponentials. Okay, so now that we've found a general solution, let's go ahead and use this, find the particular solution by using these coordinate points that we're given. Remember, these are x and y. Alright, so y equals, it's plus or minus c times the absolute value of 1 plus x squared. And we're going to use these values of 3 and negative 20. And we're going to use this to find c. So negative 20 plus or minus the unknown c times the absolute value of 1 plus 3 squared, which is 9. Get negative 20 equals, I can just drop the plus or minus for now because I'm about to find out what actual value it is. Is it positive or negative c? So the absolute value of 10 is 10. Therefore, c is negative 2. So now I know that it's negative. And that's what it meant back here about identifying positive or negative solutions where appropriate. So, particular solution, we've got the equation. It's going to be y equals negative 2 times the absolute value of 1 plus x squared. All right, similar for part C. Same idea. Y equals plus or minus c times the absolute value of 1 plus x squared, because this is the general solution we're going to use to find the particular. We're going to use these coordinate points here. Okay, 8 equals, just use c, doesn't matter, 1 plus 1 squared. 8 equals c times absolute value of 2, therefore c is 4. And this equation is y equals 4 times the absolute value of 1 plus x squared. Okay, so to the back page, growth and decay models. Quantities that grow, too many that's, or decrease by a factor or a percentage at regular intervals are exponential. This can be stated as the rate of change of a quantity, so rate of change, directly proportional to that quantity itself. So mathematically we state this as dy dx, so the derivative of y in terms of x, rate of change, equals k, some quantity times the derivative, the function y, which is the thing that we're differentiating. Where k is either a growth, because it's positive, or decay because it's negative. Okay, so solve the separable differential equations. We have dy dt equals ky. So let's write this as dy equals ky dt. I need to get this y to the other side. 1 over y dy, equals k dt, so a constant, just a number. And now we can integrate both sides. This gives me the natural log of the absolute value of y on the left here, equals, I'm integrating a number, and I'm integrating it in terms of t. So that's going to give me kt plus some c value. All right, so if we do put everything to the power of e, this whole piece here. Then on this left side, I've got the absolute value of y equals this right side, which is e to the kt plus this some c value. I've got c sub 1 there just to kind of distinguish it between the c that we're going to end up with. Just notation. Okay, so this we can write this as e to the kt times e to the c sub 1. And who knows what e to the c is going to be, but we just know that it's a constant of some description. So we can write that as the absolute value of c times e to the kt, and then it's going to be y equals plus or minus c e to the power of kt. All right, so we want to remember this. Okay, so up here it says memorize dy dt equals ky, then y equals c times e to the kt, where c is the initial amount present, usually the y-intercept of the graph. Okay, so this is important. We're going to use this in this Newton's law of cooling in this last example. So the Newton's law of cooling is the rate of change in temperature of an object. It's proportional to the difference between the object's temperature and the temperature of the surrounding medium. So let's take that first, the rate of change in temperature. So d, we're going to do capital T, dt by dt. So differentiating temperature instead in terms of time is proportional to the difference. So it's going to be k times the difference between the object's temperature and the temperature of the surrounding medium. The temperature of object minus, because it's difference, temperature of the medium, like the air, usually what we're talking about there. Okay, so there's our equation, super important, got that down. It says let y represent the temperature in F of an object in a room whose temperature is kept at a constant 60 degrees Fahrenheit. So we have our equation that's representing Newton's law of cooling. Now we're going to do it in terms of this problem, and they're wanting to use y. Perfectly fine. So I've got dy, and we'll differentiate in terms of time. The temperature changes over time. K times y minus, in this case, constant temperature of 60. So the object is y, and then the constant temperature in the room is 60. If the object cools from 100 to 90 in 10 minutes, how much longer will it take for the temperature to decrease to 80? Okay, well, we have to go ahead and separate this all out because I've got this differential equation, so I'd make it separable so that I can integrate it and come up with a general equation and then get the particular equation. So I've got dy equals k times y minus 60, a quantity, dt. I need to get the y's to the left, so I'm going to have 1 over y minus 60 dy equals k dt. And now I have to integrate both sides. Actually, let me just change colour on that. Okay, left side I'm going to differentiate in terms of y, right side I'm going to differentiate in terms of t. So in order for me to do this, I need a substitution. Go down here, let my u equals y minus 60. My dy is going to be, du is going to be dy. So I have 1 over u du equals, I'm going to integrate k in terms of t. Okay. So I've got the natural log of the absolute value of u, which is y minus 60, equals kt plus, call it c sub 1. Okay. All right, so in order for me to get to this y to solve for y, I'm going to take, or do the e, put everything to the power of e on both sides. That leaves me with, up here, absolute value of y minus 60 equals e to the kt plus c sub 1. Absolute value of y minus 60 equals, remember we know that this is going to be c e to the kt, and then y minus 60 is going to be plus or minus capital C times e to the kt. So now we're getting to our general solution here. So general solution is this equation right here. Now we're going to use this now to help us find more information so we can actually answer this problem. So as not to confuse you too much with this, because this is stuff that we've done before. For example, if we look at this little example here, we've got a biologist who's researching a newly discovered species of bacteria at time t equals 0 hours. He puts 100 bacteria into what is determined to be a favourable growth medium, blah, blah, blah. 6 hours later, he's at 450. So he starts with 100, ends up with 450. We do all this, we find the natural log, and it's literally to find the k value. That's what we're about to do with this. So it's very similar stuff in terms of like compounding interest, or in this case, growth of bacteria. It's these exponential functions. So here we've just found the general form of it, and now we're going to apply the information that they've given us. So if the object cools, here's what we need. It tells us if we go from 100 degrees to 90 degrees, it takes 10 minutes. So there's our data that we can use to find some of these unknowns that are showing up in this problem. Okay, so at the initial value, time 0, we have 100 degrees, okay? So we can use this to write 100 equals c times e to the k times our time being 0 plus 60. 100 equals c plus 60 because e to the 0 is 1, meaning that our c value is 40, okay? So now we're building more of our equation. So now we've got y equals positive 40 e to the kt plus 60. Now we're going to use the other piece of information. After 10 minutes, we want to find, or we've got 90, which is going to help us find this k value right here, so we can go ahead and solve it for when it's, how long it takes to get to 80 degrees. Okay, so we've got 90 equals 40 times e to the k times, in this case, 10 plus 60. Move over 90 minus 60 is going to be 30 divided by 40 equals e to the 10k. So I just brought the 60 over and divided both sides by 40, so 3/4. So 3/4 equals a to the 10k. In order for us to solve for k, we have to use natural logs. So we convert to natural log of 3/4. So the base is the base is the base is going to equal to 10k. You can basically take the natural log of both sides, either works. Okay. Therefore, k is going to be natural log of 3/4 over 10. So that's our k value. Okay, so we used the 100 and the 90, and now we're going to use this to find the 80. So this is the last part. We're going to finally find our answer. All right. So we have this equation, y equals 40 e to the power of natural log, 3/4 is 0.75 over 10 times the t plus 60. Now we want to find it. How long will it take? What is this t value? How long is that going to take? So I've got 80 equals 40 e to the natural log of 0.75 over t, and over 10 times t plus 60. Move it over. I've got 80 minus 60 is 20 over 40 equals e to the natural log of 0.75 over 10. Oops. Times t. So don't get hung up on this. This will be stuff that you've done before. So 1/2. I'll do natural log of both sides. And I'm ending up with natural log. So we're basically doing the natural log of 1/2 divided by the natural log of 0.75 divided by 10. And that's going to give you your t value. So we're ending up with 24.0942, so approximately 24. So 24 total to get to 80 degrees Fahrenheit. It took 10 minutes to get to 90. So final answer, here we go. It takes approximately 14 minutes for the temperature, or a further approximately another, let's put another in there, 40 minutes for the temperature to reach 80 degrees Fahrenheit, or to decrease to 80 degrees Fahrenheit. Okay, so it seems to be a lot of work here. It looks like a lot, but it's what we've been doing, and it's stuff that we have done before in terms of this K in previous classes using natural logs. Okay.